Okay, our second speaker today is Felipe Souza. He's from the Federal University of Santa Catalina in Brazil. He's fairly recently finished a master's in odor dispersion simulations, and he has been guided by his professor, Melo Lisboa, and who's also chief of the Laboratory of Air Quality Control, where he's currently working.
Good afternoon. It's a pleasure to be here. Our work was developed with three people, Professor Henrique, my fellow colleague Leonardo, and me. In this work, we compared two stationary models, AERMOD and CIMOS 97. Both of them are regulating models for two countries. AERMOD is the regulatory model for United States, and CIMOS 97 is the regulatory model for Czech Republic. We used Joseph Keder's study, where he validated an CIMOS 97 model through the Uttenweiler database. That database is a freely accessible database, and we made use of his results and reproduced his approach and his methodological technique in the comparison with his results. We chose the Uttenweiler database because it's free. It has a high amount of data, and it's got also a low stack, which is representative of a great number of real conditions. And this experiment has been tested with a great amount of models, so the results could be compared with other results. The objective of this work was so to compare the AERMOD model with the approach that was developed by Dr. Keder for CIMOS 97 model. Both models are originally conceived to model 1 hour averages, but they were adapted through a picture-mean approach to model a fewer amount of time average. So on AERMOD and on CIMOS 97, the model calculates concentrations. So on both of them, they used Stevens' power law, which is this one, to transform the concentrations predicted by the model to the intensity predicted by the model. So to compare the intensities predicted by the model to the intensities that were perceived by the assessors that were on field. The picture-mean approach used was of 2.3. We used this value because Joseph Keder also used that value, and that value is recommended in the New Zealand guideline. CIMOS 97 as AERMOD can simulate annual concentrations. It's got 5 classes of stability, 3 stable, 1 neutral, and 1 convective one, and they were developed especially for Czech Republic. And the concentrations, the emission rates were corrected to standard temperature and pressure conditions. On AERMOD, the stability is calculated through the similarity theory, and the model is not indicated for simulations farther than 50 kilometers away from the source. Both models can simulate and include the obstacle effect on AERMOD especially, it's got an algorithm called prime, which accounts for the building downwash effect. Here you have an image where after the obstacle, the plume goes down, which makes the concentrations to go up after the obstacle. So this is a brief description of the data sets that we used. There were 14 experiments on 3 cloudy days. Each experiment was 10 minutes long, and there was a sonic anemometer that measured wind speed and direction every 10 seconds. And there were also 2 tracer measurements. The tracer measure was SF6, and it was measured every 10 seconds. Sometimes 11, sometimes 12 trained assessors noted the intensity on scales from 0 to 5. And the stack area was 3.6 square meters, and it was 8.5 meters tall. The atmospheric conditions varied between neutral and stable conditions. Here's a quick map. There was a little bush area in the north. Here's the position of the stack, and here are the positions of the assessors. And here is the position of the sonic anemometer. There was also a cup anemometer on field, but on initial simulations, we found out that the sonic anemometer gave much better correlation results for the simulations. Odour and Lytle, they adimensionalized and put that experiment on a wind tunnel, and they simulated only 3 of those 14 experiments under only neutral conditions. And here's the little bush area, and here's an image, and they simulated the wind coming from all of those 4 directions. One coming from 220, one from here, and one from here. The most important direction that correlated with our real experiment was the wind direction coming from this direction, which corresponds to this image. So close to the source, this study was accomplished by Vieira de Melo et al. He compared Kalpoff and AERMOD for the wind tunnel experiment. So close to the source in the wind tunnel, both models underpredict the concentrations. Here are the measured concentrations. In red is the concentration predicted by Kalpoff, and in blue the concentrations predicted by AERMOD. And as you will see, some similar results were achieved by our group. Another experiment that was made, this one with the real case one, not with the wind tunnel experiment. They tested all of those models, including Lagrangian models, LASSAT and Alstal 2000, and some stationary ones also, as ADMS, and compared them between them using 2 statistical index, normalized mean square error and fractional bias. And the results will be shown in the last image. Here's a brief description of what Joseph Keder, the one who we based our study, did. He chose this value of peak to mean, 2.2, and he tested Simons for the Uttenweiler, Odour, and tracer experiments. It's needed to be clear that there were 2 experiments that occur. He simulated the experiment as flat terrain. The hourly concentrations were transformed into peak concentrations through the use of this peak to mean approach. And there wasn't a fit curve on the database description. So, oops. Here. He did an approach that he developed himself to establish a comparison. He simulated the concentrations. I'm going to go back a few slides. He simulated with Simons 97 the concentration for each of these positions with Simons 97. And each position corresponded to a person. So the person noted an intensity. So there was a corresponding between the predicted concentration and the intensity. So he grouped all of the concentrations that corresponded to intensity 0. And he calculated the median of that group. So he had 6 pairs of intensity and concentrations, and he tried to find the curve that best fitted those set of data. He eliminated this point because it wasn't good for the fitting curve. So we just repeated his procedure and compared with his results. Okay. Oh, I'm going back. This is just a quick flowchart of AERMOD. This arrow is wrong. AirMap goes here. The emissions go directly into AERMOD, and AERMOD calculates the concentrations. In the meteorological module, we insert the upper air and surface data and the land use data. Here are the emission rate values that we have inserted into the model. We multiplied the odor concentration by the airflow, and we obtained the odor emission rate. We made a few tests before we could get the best AERMOD configurations. I believe if we continued the tests, we could even get some better configurations. First, we compared the use of a cup anemometer with a sonic anemometer. AERMOD doesn't allow more than one meteorological surface station, so we had to choose between them, and we found out this one was better because it calculated wind every 10 seconds. So we calculated the mean value of wind direction and speed and the temperature, and we complemented those data through cloud cover, using cloud cover and pressure from Laupheim Airport, and which is 22 kilometers from the site. And we got the sounding data from the I'm not German, Schanenberg Airport, 84 kilometers from the site. Okay. The values of albedo, bound ratio, and surface roughness length that we chose were those. I just going to note that this value differs from Keder's value, which was 0.3. This may be responsible for some part of the results, though we needed to correct the wind speed and direction because the AERMOD model it rounded both of those variables. And we also inserted the deviation of wind, horizontal deviation of wind, and the horizontal deviation of the W component of the wind. No corrections were made to standard temperature pressure. We used ambient pressure. And here are the statistical analysis that we've made. We used bias. Those indexes were the same that Keder used. Bias, fractional bias, normalized mean error, correlation, geometric mean bias, geometric variance, and factor of 2. Those two indexes, they're good. They're sensible to high values, and those two are sensible to low values. But in our experiment, we had a great number of low values. This is the result for Cadder. This is the factor of 2. Just to explain, if the ratio between the predicted and the observed concentration is between 2 and 0.5, the model is acceptable. So he reached the result of 57.7% of the results. So the model didn't overpredict nor underpredict the concentrations. The first simulation that we've made, using the same peak-to-mean ratio that he used, we underestimated the concentrations, so we didn't reach as a good result as his. So we tried another peak-to-mean ratio of 6.6, which improved a lot of results. I'm almost finishing. So this is the comparison of AERMOD version with peak-to-mean 2.2, peak-to-mean 6.6 with Cadder's approach, and this is the model, perfect model, which is when the model doesn't make any mistakes, which is impossible, and those are the acceptable values. So with this approach, we could get a fairly good result. Compared to other models, including Lagrangian models, this simulation was fairly good, but I should note that the winds were not light nor low, and the conditions were all good for stationary models, so that's why they reached good results. And I should also note that these two indexes, they are sensible to high values, and in the simulations we had lots of low values. So this may be another reason why both of those models reached good results. This is the fit curve that we obtained with the data that we used on this study, and we compared this fit curve with Cadder's fit curve that he obtained, and we found out that the fit curve obtained in this study had a much stronger growth than Cadder's, and this is a theoretical fit curve, and it grows much more smoother. So this should be the real case. And just to finish, I should note that when we found out these fit curves through this procedure, we are masking part of the model errors with this fit curve. So this is not the recommended way to compare intensity and concentrations. And these were the results we obtained. As both for AERMOD, we used Cadder's fit curve and our fit curve to compare intensity and concentration, and we found out that our curve was most suited, which just attests what I have just said. For conclusions, we say that further validating studies are necessary, especially under low wind conditions when odor concentrations get higher, and AERMOD underpredicted the concentrations for this Uttenweiler experiment. The fit curve approach isn't the most adequate once it tries to correct part of the model mistakes. A better peak-to-mean approach was able to improve AERMOD's performance, and both models, Simons 97 and AERMOD, they reached good results for fractional bias and NMSE. But these indexes, they aren't so sensible to low values, which is the case of the simulations that we've made for the Uttenweiler experiment. Okay, thank you.
Thank you.
The basis was, we made an Excel, we made all of the calculations we put all of the calculations into Excel, and we tried which peak-to-mean fits best the results. that was the way that we try to correct the mistakes that Pick2Me 2.2 was making.
Right. Okay. The other interesting point was SIMOS. What was your sort of background for using SIMOS?
Actually, we didn't use SIMOS. We used Joseph Scatter's papers, and we compared our results with his.
Oh, okay.